Dear teachers, we had one module on X-ray diffraction in which we discussed about X-rays, different wavelengths of X-rays, how we produce X-rays, the materials having crystalline order, Bragg's law, diffraction, and the X-ray diffraction pattern based on a powder X-ray diffractometer. So now we will be moving to the second module in continuation of the X-ray diffraction 1. Now we have the X-ray diffraction 2. So in the previous module on X-ray diffraction, which was X-ray diffraction 1, we had discussed about the powder X-ray diffractometer, which is primarily built from three basic components. You have the X-ray source, which is normally a sealed tube X-ray source, and where these X-rays coming out of the X-ray tube fall on a sample, and then the sample diffracts, and these diffracted beam fall on detectors. Now look at the various types of detectors that is possible to have in your X-ray diffractometer. So there are many types of detectors available today. However, the cost of the detector can change, and hence it depends what kind of detector you want to use. It also depends how much accuracy you want in your measurements. Based on that, you can choose your detector. So there is a whole lot of detectors, from very simple early type of detectors which are based on proportional counter, then the most commonly used scintillation counters, and today going through all these detectors like the silicon detector, the germanium detector, the coming today the best type of detector, most sophisticated detector, are the charged couple device. So typically the most commonly used detector is the scintillation detector. The scintillation detector uses a phosphor or a scintillator. So when X-ray photons fall on this phosphor, then it creates photons from X-rays, and these photons fall on a photocathode, and then this photocathode generates electrons. These electrons fall on what are called dinodes, and they keep multiplying, and finally they fall on the anode. So from the photocathode, the number of electrons produced till the anode, you have a large increase in the number of electrons, and so the signal of the X-ray falling on the detector is amplified. So this is a scintillation scintillation detector, which is very commonly used in most X-ray diffractometers. The most advanced type of detectors are the charged couple device, which uses a phosphor screen initially, and that phosphor screen, as before, converts the X-rays to visible light, and then this visible light actually is converted to charges which records the light signal, and this is an excellent detector. It has high sensitivity, low noise, and excellent linearity of response. So this is some of the very advanced detectors people use in X-ray diffractometers. The intensity of the X-ray, as you can see, will vary, and depending on the angle of the diffraction, as also discussed in our previous module. So this is a particular material on which X-ray diffraction has been carried out and is being shown as you see it on the computer, which is connected to your X-ray diffractometer. You can see that there are several peaks, and each peak can have a number, which is basically the D value, which is being calculated by the software automatically, and this is a snapshot of your computer screen where the software, which is given along with the diffractometer, is being used to map the various reflections of the X-ray diffraction which has occurred, and you can also pull out various files as shown on the right hand corner. That is a file which you have pulled out from the software where a lot of data is stored, and you can match your X-ray with the reflections of a particular sample which is stored in the file which is you are accessing through your software. So that way you can compare the d values of your material which you have studied using the X-ray with the d values which are there in the material which is in the recorded earlier and is available to you as data to compare and match with the X-ray diffraction pattern. This X-ray pattern, here you can see that there are some red lines and there are some black lines. So, the black lines are basically the measured X-ray diffraction of a sample of what is strontium titanate, and you can see it matches with the red lines which are pulled out from the software with the data which is already recorded for strontium titanate. So, and they match well, and this is a way how X-ray diffraction is used. You measure your data on your material and you compare with the data known in literature which is available to you in the software, and then you match it and you see that all the reflections are matching. So, there is a perfect match. Now, look at all these materials and not only match them, but you can also find out details about them like lattice parameters, what are the reflection planes for each of these d values. For that, you will have to know something of what are called three-dimensional lattices and their symmetries, because every crystalline material will have a three-dimensional ordered lattice based on some symmetry, and you will have to use them when you try to index these reflections, like what is occurring at certain 2 theta. This line or this reflection is due to which HKL plane. So, there are a lot of HKL planes in crystals. So, for example, you have so many types of crystal systems. Basically, they are shown here. You have 14 Bravais lattices coming out of 7 crystal systems, and when you do X-ray diffraction, you can find out the lattice parameters, the volume, the density of your material which will fall among one of these Bravais lattices. So, you can have a monoclinic cell, or you can have a triclinic cell or a tetragonal cell, and each of these cell will be defined by a set of lattice parameters. For example, if you have a cubic cell, then the cubic cell will have A equal to B equal to C. So, you know from X-ray diffraction you have to get only one parameter which is A, and alpha, beta, gamma is also 90 degrees. So, you do not have to find, or you need only one parameter. However, if you look at the bottom, you have a tetragonal cell where A is equal to B not equal to C and angles are all 90 degrees. So, you need now two parameters. So, you can get these parameters which are called the lattice parameters from X-ray diffraction, and you can also index each of these reflections based on HKL planes. So, what are these HKL planes? Now, these are also called Miller indices. So, you see in this cube which is drawn, if you take the lattice plane which is shaded in green and you want to index the pattern, then this plane has to be assigned 3 numbers, and these numbers are HKL and are known as Miller indices. And how do we find out? We look at the intercepts of these plane with the ABC axis. So, you can find out the Miller indices in first finding out the intercepts along each of these axes. Along the A axis the intercept is 2, along B axis it is 3, and along C axis it is 1. So, that is how you get 2, 3, 1. And if you take the reciprocals, you will get 1 by 2, 1 by 3 and 1 by 1, right, and then you convert them in the smallest integers possible, and so you will ultimately get the number 3 to 6. Hence, this 3 to 6 is actually the Miller index of this particular plane shaded in green. And this 3 to 6 reflection plane, when X-rays interact with these planes, they will give rise to a peak which will be a function of some theta, and that particular peak you have to identify somewhere in this pattern, and then you can say that is 3 to 6 for that material. So, that is how in a powder X-ray diffraction pattern you will get a set of reflections as a function of theta. Each set of reflection can be assigned some Miller indices or set of planes, and that is called indexing the X-ray pattern. Once you find these indices for all the reflections in the X-ray pattern, then you say that you have indexed the X-ray pattern. That is very important in powder X-ray diffraction. So, that is what we are talking, indexing of the powder pattern. So, every material will have some crystal system, and based on the crystal system you will have various symmetries, and the symmetries will tell you how many types of lattice parameters you need to know, whether you need to know ABC or only A, etc. And all crystals will have to be indexed based on their reflection planes, and the reflection planes will have some Miller indices like shown here. You have 100 plane, you have 200 plane, and each reflection plane will have a D value which is mentioned as DHKL. So, for every HKL plane you will have a DHKL. So, for 200 you will have D200. And now there are some relationships by which you need to do the calculations. For simple systems like cubic, the equation is very simple, 1 by d square HKL is equal to h square plus k square plus l square divided by a square. Similarly, for tetragonal it is easy, not too difficult. You need two lattice parameters for tetragonal, A and C, and then it is related to HKL parameters, right. The equation is shown to you here. But for a difficult crystal system is like triclinic, you have all the lattice parameters you need, A, B, C, alpha, beta, gamma, and so the equation becomes little complicated. So, it is not always possible to index all the lines of a powder X-ray diffraction pattern of an unknown material very easily, unless it is a cubic or tetragon, etc. Most of the time powder X-ray diffraction for unknown materials to solve is challenging and a difficult process. Most of the time we are trying to compare materials with known materials, whether that is present in our powder or polycrystalline material or not. So, if known materials are there and the database is with us, we can compare, and even from a mixture of three materials we can identify what are the three materials, and from the intensity of the reflections we can semi quantitatively also tell how much of each material is present in the mixture. So, there the intensity of the reflections will become important. So, from the powder X-ray diffraction pattern you can index the all the lattice, all the reflections, if you have a good understanding of the crystal system and you know how to index the planes using the Miller indices. Now, to go into more detail, the intensity of the reflections that you are getting depends on what is called the structure factor, and the structure factor is related to the scattering factor and the phase. So, these are more details. The intensity is important, and if you want very quantitative values of intensity to be compared to find the structure and atomic positions, then you really need to know these things very accurately. So, the structure factor, the scattering factor, there is multiplicity factor which is related to number of equivalent scattering planes in a powder X-ray diffraction pattern. You need to understand what is called the polarization factor, and that is given by the equation below, where it is a function of theta. So, these affect the intensity of the reflection from individual HKL planes, and that one has to know if you want to do a quantitative analysis of your X-ray diffraction intensities. You may have to add some additional factors which depends on the geometry of and many other things like the Lorentz factor or the polarization factor, the absorption factor. The material may absorb X-rays, and so you may have to put an absorption correction, because that will affect your intensity. And there is something called temperature factor. That means atoms are not in the same position, they are vibrating about their mean position, and that will cause what is called diffuse scattering. So, there is something called temperature factor. So, these also have to be built in if you are looking at working with the intensity of the X-rays in a diffraction pattern and trying to do a quantitative calculation, then all these factors have to be taken into account. The structure factor actually is given by such an equation. So, if you have an HKL plane in which there are certain atoms. Now, if there are n number of atoms, then each atom will have a scattering factor that is given by small f n. The total structure factor is given by capital F HKL, and on the right side you see it is a summation of scattering factors small f n and a phase which is given by e to the power 2 pi I h u n k v n l w n, where u, v, w are coordinates of the atom. So, it can be the coordinates of the atoms in the lattice, and these are very important when you want to calculate the structure factor, which is related to the intensity. The intensity is proportional to square of the structure factor, right. So, I is proportional to square of the magnitude of f, and the structure factor is actually related to the scattering factor and this exponential factor. The exponential factor has the phase component. So, there are two parts of the structure factor. The one part is the scattering factor, the other part is the phase, and both are very important in giving you a structure factor. A big structure factor will give you a high intensity. So, the scattering factor and appropriate phase are related to ultimately to the intensity of the reflection coming from a particular HKL plane. For each individual atom, there is a particular scattering factor. So, for hydrogen, there will be a scattering factor. For an element like boron, there will be some other scattering factor. And scattering factor depends on the number of electrons in the system. Okay, so higher the number of electrons, the scattering factor is higher. Of course, the scattering factor also changes depending on which X-ray you are using. So, you are using X-ray of particular lambda, you will have some scattering factor. So, f depends on sin theta by lambda. It depends on the angle at which you are looking at the scattering. It depends on the wavelength of the X-ray which you have used to look at the scattering. As in the structure factor equation, you see you have this capital F, which is the structure factor, is related to small f multiplied by a phase factor. If we use this, we can come to some conclusions, like for a body centered Bravais lattice, it has to be that H plus K plus L has to be even. This we can prove by using this structure factor equation, because something in that equation in the exponential part will make that term go to 0 if H plus K plus L is odd, and hence you see certain reflections will become absent. Okay, these are called systematic absences. Similarly, for a face centered lattice, H, K, L should all be odd or all be even, and this we can conclude from our structure factor equation. So, this is what is listed, that what are the permitted reflections. For simple cubic, you see all the reflections are permitted. You have 100 is allowed, 110 is allowed, 111 is allowed, 200, all are allowed, there is no restriction. Whereas, for a body centered cube, you have restrictions. That means 110 is allowed, but 111 is not allowed. 200 is allowed, but 210 is not allowed. Again 211 is allowed because 2 plus 1 plus 1 is even, and that is allowed by the argument which we discussed based on structure factor. Similarly, for FCC system, all the HKL, all of them should be odd or all of them should be even. So 111 all are odd, so it is allowed. 200 all are even is allowed, but you see 110 is not there because 1 1 are odd, whereas 0 is considered even, and so you cannot have odd and even in an FCC structure. Hence, we can understand systematic absences if we understand the structure factor relation, and we can derive these from structure factor relationships. Okay. So, that is very important when we are calculating why certain intensities occur, why certain reflections do not show up based on structure factor calculations. So, this is an example. Suppose you have a simple cube and I want to do a structure factor calculation. So, I have to look at the coordinates which are given in the exponential 2 pi h x k y h z. Now, my x, y, z here are my coordinates. So, for a simple cube, the coordinates are 0 0 0. That means the atom is at 0 0 0 position, and by symmetry all the remaining atoms are generated. So, if I put the value 0 0 0 in my exponential, then e to the power 0 is 1. So, my left hand side becomes capital F and my right hand side becomes small f. So, that means my structure factor will become proportional to f and intensity will be proportional to f square. That means this reflection will be valid and will be intense. So, it is independent, you can take any HKL will become allowed. However, for a body centered structure like that, where there are two atomic positions to be taken care of, one is the atomic position at 0 0 0 and the atomic position which is at the body center, which is at half half half. That means x, y, z are all half half half. So, if you put these two values in your equation, for the first one 0 0 0, you will just have e to the power 0, which will be 1, and for the next one you will have e to the power I 2 pi half h plus half k plus half h, and if you do the calculation you will see e to the power I pi h plus k plus L if you want to make it real, and then h plus k plus L has to be 2 pi. So, that is why in a body centered has to be 2n, that means it has to be even, then only this will be a real number. So, h plus k plus L has to be even, that is why for a body centered system you need to have h plus k plus L to be an even number. So, that is what we prove. So, if you have this h plus k plus L even, then the structure factor will be equal to 2 scattering factor f, and so the square of the structure factor will be 4 f square, whereas if it is odd then it will go to 0. Then from X-ray diffraction pattern, other than indexing the pattern, getting lattice parameters and calculating the intensities which can be used for ultimately finding atomic positions, if you are able to calculate the structure factors properly, then you can do that. You can also do one thing which is very popular in materials which form alloys, like you have two metals, silver and gold, forming an alloy. So, silver has a lattice parameter of 4.0786, gold has a lattice parameter somewhat different from silver, but if I make an alloy of gold and silver and I do an X-ray diffraction, then I will get a lattice parameter which is in between the value of gold and silver. And so, I can find out the composition of my alloy by just doing the powder X-ray diffraction. So, if I draw a plot of the lattice parameter obtained from different alloys, then I can find out by drawing a vertical on the x axis that what is my composition. So, I have at one end 4.0786, on the other end I have 4.0862. Now, suppose I get 4.0792, which is in between the two, I can draw a line on the vertical on the x axis and I can tell you what is my composition of silver and gold. So, this is actually called Vegard's law, where you have a lattice parameter which is in between the lattice parameter of your end members, which are the two alloys. So, I can which are the two pure metals, and once I make an alloy, I can find out the composition of the alloy from powder X-ray diffraction. We can also find out thermal expansion coefficients. So, if you have a disordered system and you change the temperature, then disorder will increase. So, you measure the lattice parameter from powder X-ray diffraction at some temperature, say 25 degrees Celsius, and the lattice parameter is 4.1023, and you change the temperature to 35 degrees, and the lattice parameter you again measure using X-ray diffraction, and it goes to 4.1031. And with the simple equation given below, you can then calculate alpha, which is the coefficient of thermal expansion, and this is an important number which you can use as a property of the material which you are studying. You can study order disorder through powder X-ray diffraction. So, if you have an ordered structure and a disordered structure, by varying the temperature and you take X-ray at lower temperature and higher temperature, then you will see that you will get additional reflections or additional lines in your X-ray diffraction pattern when it is ordered. When it is disordered, you will have less lines. When it is ordered, you will have more lines. So, you can study such ordered disordered structures typically in many materials. One example is of this copper mercury iodide, and which changes this order disorder at 80 degrees Celsius. But there are many alloys also where you can study this order disorder transition. You can study non-stoichiometry in solids. For example, you take zinc oxide, you take the X-ray, you know its lattice parameter. If you heat zinc oxide, then you find that some of the oxygen will go out and you will have a composition like zinc 1 plus XO, and actually the color changes from white to yellow. And from X-ray diffraction, now if you calculate the lattice parameter, that will be different from the lattice parameter which you have calculated with the from the X-ray diffraction of zinc oxide before heating. And from the lattice parameter, you can calculate the density, because you know from the lattice parameter the volume, and from that the number of atoms is there. And so, using this equation which is given to you, you can find out rho and the density change for a non-stoichiometric solid. Why we are saying non-stoichiometric? Because zinc and oxygen are now not 1:1, it has become 1 plus X to 1, because some of the oxygen has gone. So, you can tell the type of defect which is present in such non-stoichiometric solids by using the X-ray diffraction technique to find out the lattice parameter, and from the lattice parameter you find out the density, and you compare the density before heating and after heating, and you can discuss the non-stoichiometry in the compound. Then there are things like, if you have polycrystalline materials where the tiny crystals are all oriented along certain direction, then you will have some reflections very strong. So, if most of the crystals of a material are layered, then there is a tendency for them that you will see them lying along the flat planes. So, you will see reflections which are the 0 L reflections will be very intense, and so you can say that this material has a layered kind of structure, because they have a tendency to lie along certain directions, and this is reflected in the intensity in the of certain particular HKLs, which is gives rise to what is called preferred orientation effects, and that we can study using X-ray diffraction. You can also calculate what is called particle size, but to be more precise, crystallite size from X-ray line broadening study. And there you take a particular reflection, one reflection at a particular theta value, and then you measure the full width at half maximum, and you use the equation which is given below. beta is equal to lambda by T cos theta. So, here you have to use your material for whom you are finding out the crystallite size, and you need a model material whose crystallite size is quite large, say in microns, and then you can do this measurement. So, here you will have to use this equation and calculate T. So, here beta is related to full width at half maximum of two materials. It is the difference of two materials. So, you can maybe more clearly understand here that the equation T, where it is written grain size, or more correctly the crystallite size, is given by 0.9 lambda equal to b cos theta, but this b is equal to under root of b square m minus b square s, where bs is your some material whose size you know, which is large size particles, and the bm is the full width at half maximum of your sample. And so, these two numbers are required to find out b. Once you know b, then you can calculate the grain, the crystallite size, using the equation 0.9 lambda by b cos theta, and this is called the Scherer's formula. So, you can see that out of your X-ray pattern, where there are a lot of reflections, you select one reflection and measure the full width of at half maximum, and then compare it with another material whose particle size or crystallite size is very high, and then you can get the crystallite size of your material. So, this is very important in all materials, where especially in nanomaterials, where you are trying to find out the size of the nanoparticles. So, from powder X-ray diffraction, you can also find out the positions of atoms or the exact structure of the atom, but this is a little difficult and you need very high quality data. You need X-ray to be collected using primary monochromator, so that you have very high intensity. And so, this method of getting very high quality data and then doing refinement was developed by Rietveld, and hence it is called the Rietveld refinement, and this is a detailed procedure where you fit the entire diffraction pattern to a model diffraction pattern, and this requires a software to minimize the difference between your pattern and the model pattern whose crystal structure you have an idea, and you compare the two and minimize the difference. And this whole program of doing Rietveld refinement was developed first by Rietveld, and it has gone through lot of development, but the first requirement is that you need very high quality powder X-ray diffraction data, where primarily we need very precise wavelength of the X-ray, and typically you use primary monochromators in these X-rays. So, the method involves minimization of the differences of the various intensities at each theta value. So, there are several equations which you minimize using a software which is developed, and it depends on the type of diffractometer and your choice of software. There are softwares which come with the machine, there are softwares which are free, you can download them, and you have to minimize these procedures. One has to learn by practicing the refinement procedures. Basically, you are trying to fit your pattern to a model pattern, and you come out with a number, the R value, what we call, or the reliability factor, which should be as low as possible. So, there are a reliability factor which is called RP, or reliability factor like RWP, and which is called the weighted reliability factor, or the simple reliability factor called RP, and these have to be minimized, and minimized, the better you minimize, that means the lower the number, the better is your fit to the real your data, to the model data. So, this is how you do Rietveld refinement and try to find out the structure of a material of which you do not know, or you find out the atomic positions, etc. This is not very trivial, and this requires very high quality X-ray diffraction data. So, these are some more equations which are showing you the type of functions one uses to fit the profile. So, you use what are called pseudo void function, which is a combination of a Lorentzian or a Gaussian, the L and G. So, there are many types of mathematical functions one can use to fit the powder diffraction pattern. So, this requires some detailed training and understanding of these mathematical polynomials. So, for example, the polynomial can be what is called a shifted Chebyshev polynomial, or it can be a pseudo void polynomial. But these polynomials are basically combinations of mathematical functions which mimic the X-ray diffraction pattern that you have measured using the powder X-ray diffraction machine. But this kind of analysis is very detailed and needs lot of experience and lot of understanding about the reed field refinement process. So, this is a typical plot one gets when you do the reed field refinement. So, you can see that there is some green lines and there are some red dots, and so one is the measured data, the other is the model data. They are put one on the other, and you can see in the bottom there is a purple line which is called the difference pattern. The difference pattern should be a straight line, that means there should be no wiggles, but if there are, that means the model and your measured data have some differences. In you cannot have absolutely complete agreement with model and experiment, because there will always be some difference, but the difference has to be minimized. So, if you have lower wiggles or less the intensity of the difference pattern, that means your model is you have got a good fit to the model. So, in this case it looks like a good fit, and also you calculate these numbers which we mentioned earlier, which is the RP factor. As you see, it is like 4.84, which means the difference between the data measured and the model data is a 4% error is there. So, which is not bad for powder X-ray diffraction pattern, and there are other statistical numbers like the chi-square fit, etc. So, with all these things one can conclude whether your model structure is the real structure of what you have measured using X-ray diffraction. So, this is a typical X-ray diffraction pattern showing the reed field refinement and the fit to the reed field refinement. The difference plot all are shown in this figure. So, using powder X-ray diffraction, we can do many things as we discussed. We can calculate lattice parameters, we can use reed field refinement to find out the structure. Typically, X-ray diffraction is a non-destructive technique. So, it is good because it preserves your samples. They can be applied to polycrystalline samples, and you need small amount of sample to do the X-ray diffraction. You can identify various phases even in a mixture of phases. For example, you have say different types of titanium dioxide. So, you can look at the X-ray diffraction of the mixture and say that this is anatase or brookite and rutile, etc. You can do quantitative phase analysis using X-ray, but then the intensities of your reflections should be very perfect. That means you have to make lot of care to apply appropriate corrections, etc., and use preferably copper K alpha 1 or whatever K alpha 1, one type of wavelength which has very little spread in lambda. You can determine the crystallite size from the broadening of the peak, and you can also do structure determination in cases where you have very good high quality X-ray data using reed field refinement. There are certain limitations. For example, you cannot use powder X-ray diffraction to find out local structure, for example, in amorphous compounds. You cannot detect if you have in a mixture some component which is very small amount, say less than 5% of the total material, then you will not be able to really detect those material. In cases of preferred orientation, you may get wrong values for the intensities. and then you may get wrong idea about the crystal structure. Of course, the preferred orientation can be removed by either rotating the sample or grinding the sample. Materials which absorb X-rays are then not very good candidates for doing powder X-ray diffraction, and that depends on its absorption coefficient mu, and depending on that then you have to choose other techniques. And finally, structure determination from powder X-ray diffraction is very difficult and is not always possible, which is possible using single crystal diffraction. So, that is another technique which uses X-rays, but it uses single crystals, and their structure determination is much more easy. So, we have come to the end of this 2 lecture module on X-ray diffraction, where we saw how X-rays, which are part of the electromagnetic spectrum having wavelengths of the order of 1 to 3 angstroms, can be used to look at materials which have long range order, that means they have 3-dimensional periodicity, and we can find out the details of these materials, the lattice parameters from which planes the X-rays are being diffracted, and in more careful measurements we can find out even the atomic positions using X-ray diffraction. We can find out easily the crystallite size of the materials, very useful in today's world of nanomaterials. You can find out mixtures of phases. So, you can find if something material has been adulterated or which is solid and crystalline. So, you can take 2 pharmaceutical crystals and find out if they are anything else has been added. So, many such structural aspects can be investigated using X-ray diffraction, and I hope you have enjoyed the 2 lectures, and I hope you will take further interest in this area of X-ray diffraction. Thank you very much.